Let's see integrator. So this is one of the applications of op-amp. So we know the integrator, the basic mathematical formula. So if integral sin x dx that is equal to minus cos x plus c, integral cos x dx that is equal to sin x plus c. If you are giving sine as an input, we should get negative cosine signal as an output. If we give cosine signal as an input, we should get positive sine signal as an output. So this is the circuit for ideal case for the integrator. So in the input side, there is one input resistor is connected. In the feedback path, one capacitor is connected. Compensation resistor is connected in the positive terminal. So output voltage that is equal to 1 by R1 CF integral VI into dt. The nodal equation at node N is given as VI divided by R1 plus CF into dV0 by dt equal to 0. CF into V0 divided by dt that is equal to minus VI divided by R1. By the way, minus VI divided by R1 CF, by taking in integral on both sides, we will get the equation number 1, where V0 of 0 is the initial output voltage. So the negative sign refers to it is an inverting integrator, and a compensation resistor is used to reduce the input bias current, and low pass RC network is connected in the integrator. RC equal to tau, that is a time constant, we know that. It should be large for the integrator. According to the Miller's theorem, the effective input capacitance CF equal into 1 minus AV. AV is the gain of the op-amp. Equation number 1 in the phasor notation means V0 of S that is equal to minus 1 by R1 CF into 1 by S into VI of S. By putting S equal to j omega, we are getting the transfer function, the magnitude of the gain that is equal to V0 of j omega divided by Vi of j omega. So finally the equation number 2, 1 by omega R1 into CF. So this is the transfer function, frequency characteristics of ideal case and practical case. So F equal to 1 by 2 pi RF CF, FB equal to 1 by 2 pi R1 CF. If omega equal to 0 in the equation number 2, gain will be infinite or saturation condition. At the DC, the condition, if you are giving low frequencies, the feedback capacitor charged fully and it behaves as a open circuit. There is no negative feedback. The op-amp will be operates in open loop condition. By the way, gain will be infinite for ideal case. It will be does not equal to infinite in the practical case. If the gain increases, the frequency also increases. It is no problem in integrator as in differentiator. So practical integrator at low frequency gain becomes saturated. In order to avoid that, it can be avoided if CF is parallel with RF. The slight modification is done in feedback side. So the RF is connected parallel with the CF. The compensation resistor is equal to R1 parallel RF. So, approximately it is equal to R1. By doing the analysis, the nodal equation at node A, VA by R1 plus CF into dV0 by dt plus V0 divided by RF equal to 0. CF is parallel with the RF. It will be dissipation. It is also called as lossy integrator. The feedback resistor limits low frequency gain that is equal to minus RF by R1 and it provides DC stabilization. In phasor notation, the output voltage will be given as, finally by doing some approximation and simplification, we are getting minus Vi by some of the terms will be cancelled here. After simplification, we are getting this equation minus Vi of S divided by R1 by RF plus S into CF into R1 by putting S equal to j omega and doing some simple mathematical analysis and approximation simplifications. finally we are getting modulus A, that is equal to R of by R1 whole divided by 1 plus root of 1 plus omega R of CF the whole square. So finally at f equal to Fa, modulus A will be 0.707 into R of by R1. So we are getting R of by R1 divided by root 2. At Fa, integration will be start if F in input frequency is less than Fa, the circuit will be access inverting amplifier. There is no integration will be done. If F input frequency is equal to Fa, 50% of accurate result maybe we can get. And if input frequency is equal to multiples of 10 multiples of Fa, means 99% of accurate result we can able to get. So at the initial condition we can use switch in the input side. So ganged switch also can be used. This is the improved version. So some of the sample input model is given here. If you are giving sine wave, we will get a cosine wave, negative cosine wave. Square wave means triangular wave, we will get an output. If you are giving triangular wave as an input, we will get sine wave. If we get step signal, we will get ramp signal as an output. So this is about integrator.